Okay, so continuing from last time, what do we have? We have our correlation transformed variables, and we had a formula for B star, right? So B star is equal to, just like before, X star transpose X star inverse X star transpose Y star, where the star means they undergone the correlation transformation. So X, and I should probably have, no, this is the matrix. Yes, so this is the matrix X star. So X star, we saw last time, X star. You will, so here I have X1 star. I'll just do it like this. And here I have X P minus 1 star. So the P minus 1 predictors have undergone the correlation transformation, which means I've subtracted their mean, divided by their standard divided that centered result by the standard deviation of the vector, and then divided that by the square root of n minus 1. So that's what each of those are. And of course, y star is just the vector y star. So we said last time we showed that we could also write this b star equals rxx inverse ryx, where rxx is equal to this correlation matrix for the predictor variables. Now, this is the these are the original predictor variables. Okay, so this is where R, say, KL is equal to correlation of XK and XL. Okay, and RYX is equal to just R, let's see, Y1 or 1Y and RY P minus 1, where RYK equals correlation of Y and XK. Okay, so I have B star. I can get it this way if I transform all these variables. Or I don't even need to transform the variables and I can find the B star, right? Because this is all based on the original variables, just the simple correlations of all the original predictor columns. And so I can get B star without even transforming the variables. Okay, that's kind of interesting. Now, also, we suppose we want to get B from B star. Well, just as BK was equal to this simple scalar multiple of little b, beta k. Beta k is equal to this multiple of beta k star. You can show, not hard to show, you can show that bk equals sy over sk bk star. Okay, so also, if I have bk or bk star, I can get the other one. So I can actually, this is a different way to compute the coefficients, the little b's. Even apart from normalizing and standardizing and doing the correlation transformation, I could compute the simple correlations of the original variables here and here with the response, and then I could compute B star this way and then multiply it by S, for each little b I want, I could multiply it by sy over sk. Now, if you thought about it, you'd say, well, what about little b0? There's no little b0 star, so we need to specify but this is always true. If I know all the other little b's, I know b0. So b0 is just equal to y bar minus the sum k equals 1 to p minus 1 bk xk bar. Because the means of all the variables have to lie exactly on the regression plane. Okay, so you can get little b0 back that way. It's interesting, right? You don't need to actually use the lm command to actually find the little b's. Okay, but really, how does this help us with our work? You know, with understanding, say, with more the applied idea of why we're even doing all this work. Okay, so to that end, let's see. Let's just, I wonder if I should do this here while I'm here. Yeah, I think while I'm here, let's just do one more thing, and then we'll get back to that, the idea of an example. So one more thing to note is, so while also, sorry, I'm jumping around a little, I know. So also, how to prove this is, one way you can prove this is that, and maybe you don't like this as a proof, but especially if you're taking Math219, I want to point this out. Since the BKs are maximum likelihood estimators for beta Ks as well, we have this result that says maximum likelihood estimators are invariant estimators, which means if BK star estimates beta K star, and I have some function of beta K star, which beta K is, then that same function of BK star is an estimator, is a maximum likelihood estimator for beta K. So in other words, no matter what I wanted, say I wanted something that was beta K star cubed times 100, I could just take little bk star cubed times 100, and that would give me a maximum likelihood estimator, also a least squares estimator for that. Okay, we're getting to the end here. So look, one more thing. Suppose I have, we just want to check something. So suppose, let's write this. How does the correlation between the predictors enter the estimated model Well, we just saw this is how this is related to the bees. But is there a way to understand correlation between predictors and the fitted model? So let's look at the case. So let's consider the case where p minus 1 equals 2. So I have two predictors. Then I have b star, right, is equal to our xx inverse and our yx. Okay, and this is only, there's only two predictors. So here I can write this as 1, 1. This is just the coefficient of simple correlation between the first predictor and the second predictor. So I can write this here like this, inverse, and this vector here is just the coefficient of simple correlation between y and x1 and y and x2, like that. I can take the inverse of a 2 by 2 matrix without going through too much of a headache. So this is just 1 over the determinant here, which is 1 minus r12 squared. And over here I get these flip around, these get negated. And multiplying through, I see that I have B1 star is equal to RY1 minus R12 RY2 all over 1 minus R12 squared, and B2 star is equal to Y2 minus R12 RY1 over 1 minus R12 squared. Okay? Yes. You see, I just did matrix multiplication here and divided by this. So this is each. So let's just look at this equation. Look at B1 star for a second. I see that B1 star, now look at these and think of them as correlation. How Y is correlated with the first predictor, how the first and the second are correlated, and how Y is correlated with the second. Well, a few things to notice. First of all, suppose R12 is 0, so that x1 and x2 are uncorrelated. Wow, look at that. B1 star is just equal to the correlation. This is 0 then, and this is 1. So then B1 star is just equal to the correlation of the response with the predictor. Okay? All right? So that's one thing to notice. Now, same thing here, right? If R12 is 0, I just get how B2 star is just how Y is correlated with X2. Now, if X1 and X2 are correlated, this is not true anymore. It gets messier. And this is the topic of the last section from Chapter 7 on multicollinearity, which is when predictors are correlated. When they're correlated, you see it gets messy. It's not cleanly this anymore, and you can think about why it would be this. But rather than do that now, we'll wait. But it does get messy up in the top, and then on the bottom as well. This gets small, so the whole thing blows up. This is something to think about. This gives you this nice separation here. So also from this, we could even find B1 and B2 and B0. So from here, you could get B1 by just multiplying by the ratio of the standard deviation. So we see also B1 is just equal to SY over S1 times B1 star, etc. So the point being, a couple points. One is you can just work with correlations and find everything, find your regression coefficients. So you still need to go back to for other things like S of B1 and things like that. Okay, one more on this about an example.